Good morning, grade 9. This is the first of your online video lessons, so please make sure that you have your workbook, you're ready to write the title and objective the same way that you normally would, and you're completing the activities on the day that you would normally have science, okay? So for this week, this is going to be the first of 3 lessons that you do. I'll explain a little bit more about what each one will entail, but we'll start with this today. So for a starter activity, can you look at the image that's on the screen now, please, this image here, and write down something that you see, something that you think, and something that you wonder. You can pause the video and just write down your thoughts now, please. Okay, so I'm going to try and imagine the types of things that people would have said. I think that they would have seen a big orange ball in the middle of the screen. They would have seen lots of other circular balls. I imagine that people would probably use the word orbit to say that they are moving around the big ball in the middle of the screen. When asked what you think, I think people would say that they think that that is our sun, that they think that these are our planets. Okay, and types of things that they might wonder would be whether or not it is to scale. So is Earth really almost the same size as the Sun? I think people would wonder if this is Saturn, and they might wonder what the rings are outside Saturn. What are they actually made up of? They might wonder why all of these planets are in the same plane. That means in the same direction. So why is it that the orbits are not all up and down and they're all in the same direction? Okay, so just to let you know what we will be looking at today, this is your title, and again you should be writing this in your workbooks, please, with today's date. So you're going to write down the title, gravity and motion, and then the learning objective for today is to be able to describe how planets orbit the Sun. I could have said here how planets orbit stars, but I've just used the Sun as our example of a star. So everybody needs to be able to define gravity. Most should be able to explain how gravity keeps objects in orbit, and then some will be able to research the orbits of comets and asteroids and create a presentation. Everybody is going to create a presentation, okay, but only some of you, I think, will get on to looking at comets and asteroids and how they are a little bit different. So please make sure you pause the video and write down your title and objective and today's date. Thank you. Okay. Just some concepts here about gravity, and we're going to watch a couple of videos as well to help to explain this. So gravity has an associated force field, okay? We assume a situation between 2 masses, so we have a mass over here, mass A, and a mass B over here. Both mass A and B have a force field, a gravitational field. B experiences a force due to A's field, and A experiences a force due to B's field. Those forces are going to be different, and they're going to be different because of the size, or therefore the mass, of each of these circles that are representing planets. Okay, so key point would be the bigger the mass, the bigger the gravitational field strength. Again, can you pause and just write down notes, please? Okay, so your research task is going to be the following. You're going to create and upload a poster, and I would like you to upload an image of your poster onto ManageBack, please, which has a diagram of a planet orbiting a star. Doesn't have to be one of our planets. You can choose any planet that you want. Okay, it doesn't have to be our sun. You could choose a different solar system if you want to do some research about that. What I want you to do is add an explanation to your poster of why the planet is under the influence of the star. You're going to explain why the planet moves in circular motion. To help you be able to do that, we're about to watch a couple of videos, and you'll be able to take notes from those videos. As an extension, okay, some of you might be able to explain how and why the orbit of a comet is different to the orbit of a planet. So what is it that happens with comets? You could do a bit of research about some comets that come into our solar system. So Halley's Comet is one that's pretty interesting, and look at the dates that we see that in our solar system. Okay, so we're going to watch a couple of videos. Again, you should pause those videos and you should write down notes for them. Today's lesson, so lesson 1 of this week, is really going through this video and you can start to do your research. Lesson 2 this week is going to be all about completing this research task. Okay, and then you can upload that to ManageBack.
By the end of this video, you should be able to describe the difference between planets, their moons, and artificial satellites. Okay, I'm showing here the Earth orbiting the Sun. Scientists call this a circular orbit, as the Earth follows the path of a circle. Now, strictly speaking, planets actually orbit the Sun more like this. Scientists call this an elliptical orbit. However, in this video, we're only looking at circular orbits, and I should point out that the Earth's orbit is virtually circular. The force of gravity acting between the Sun and the Earth holds the Earth in its orbit, and the arrow shows the force of gravity. So the key point is that planets orbit the Sun, and the force of gravity holds the planets in their orbits. Okay, I'm showing you here the Moon in a circular orbit around the Earth. Now the Moon is a natural satellite. Once again, the force of gravity holds the Moon in its orbit. Okay, this shows an artificial satellite, for example the type used for satellite TV. Artificial satellites are man-made. Geostationary satellites orbit once every 24 hours. This means that they always point to the same part of the Earth. However, other artificial satellites orbit more frequently. Now, as we said before, the force of gravity holds objects in their orbit. A key point is that in the case of circular orbits, the force of gravity is leading to a change in velocity, but not a change in speed. Remember that velocity is the speed of an object in a given direction. This red arrow shows the direction that the object's moving. As you can see, the direction is constantly changing, so this means that the velocity is constantly changing as well. However, you'll notice that the speed is constant, so the force of gravity is changing the velocity but not the speed.
Okay, the second video takes you a little bit more into detail about Newton's forces. Okay, we know that Newton is a unit of force, but how did he discover, how did he come up with his discoveries about how planets behaved in space?
When people say that Isaac Newton completely transformed the field of physics, they really aren't kidding. Now, we've already talked about his 3 laws of motion, which we use to describe how things move, but another of Newton's famous contributions to physics was his understanding of gravity. When Newton was first starting out, scientists' concept of gravity was pretty much non-existent. I mean, they knew that when you dropped something, it fell to the ground. And from careful observation, they knew that planets and moons orbited in a particular way. What they didn't know was that those 2 concepts were connected. Of course, just like with motion, we now know that there's a lot more to gravity than what Newton was able to observe. Even so, when it comes to describing the effects of gravity on the scale of, say, our solar system, Newton's law of universal gravitation is incredibly useful. And it all started with an apple. Probably. Odds are you've been told the story of Newton's apple at some point. The story goes that one day he was sitting under an apple tree in his mother's garden when an apple fell out of the tree. That's when Newton had his grand realization that something was pulling that apple down to Earth. And that led to another idea. What if the apple was pulling on Earth too, but you just couldn't tell because the effect of the apple's force on Earth was less obvious? A few years later, Newton was sitting in the same garden when he had another stroke of inspiration. What if that same force that pulled the apple to the ground could affect things much farther from Earth's surface? Like the moon. It was kind of counterintuitive because the moon orbits Earth instead of crashing straight into the ground like an apple that falls off a tree. But Newton realised that the moon was still being pulled towards Earth, it was just moving sideways so quickly that it kept missing. That was what was keeping it in orbit. If gravity was keeping the moon in orbit, what if it affected the behaviour of any 2 objects, like a planet orbiting the sun? That's the official version of the story, the one Newton himself used to tell. Most historians think he was embellishing at least a little, but there probably is some truth to it. Whether or not the thing with the apple actually happened, Newton thought that his idea seemed promising, the idea that gravity might affect everything, including orbits of other planets and moons. So he started looking for an equation that would accurately describe the way gravitational force made objects behave, whether it was an apple falling on the ground or the moon orbiting Earth. Newton knew that however this gravitational force worked, it would probably behave like any other net force on an object. It would be equal to that object's mass times its acceleration. The mass part was easy enough. It would just be the mass of an apple, or the moon. It was going to be a little harder to figure out the factors that were affecting the acceleration part of the equation. The first thing Newton realised he'd have to take into account was distance. When an object is close to the Earth's surface, like an apple in a tree, gravity makes it accelerate at about 10 metres per second squared. But the moon has an acceleration that's only about a 3,600th of that falling apple. The moon also happens to be about 60 times as far from the centre of the Earth as that apple would be, and 60 squared is 3,600. So Newton figured that the gravitational force between two objects must get smaller the further apart they are. More specifically, it must depend on the distance between the two objects squared. Then there was mass, not the mass of the apple or the moon, but the mass of the other object involved in the gravitational dance. In this case, Earth. Newton realised that the greater the masses of the two objects pulling on each other, the stronger the gravitational force would be between them. Once he had taken into account the distance between two objects and their masses, Newton had most of his equation for the way gravity behaves.
Okay, so now that you've watched the videos and you've taken a few notes on those, you should start to plan your research task. Okay, because this is research, you do need to make sure that you keep a note of where you're getting your sources from, and please make sure that you are using good sources. You don't need to upload a bibliography, but if you could just bullet point in your books, please, the places that you have got your information. Okay, thank you very much. Bye-bye.